what you want. I'll be that girl for a month, but the worst is yet to come. Check my phone. I got it like 5 texts.
God. You gotta stop texting and driving.
It's fine, we're just at the red light. There's a traffic jam right now. Oh my god.
Oh my god. Stop.
It's at the house. Okay, it's gone. It's not a big deal, it's fine. Alright, I'm good. We're good.
Excuse me, ma'am. This is Officer Osgood with the Calculus Police Department. Do you have your license to derive?
You forgot the negative.
So for our next unit, we're going to talk about derivatives. So what a derivative is the rate of change of a function at a certain x value. And before we get to derivatives, we're going to talk about the average rate of change over time. And the way you find an average rate of change is you take the slope of a secant line. So what that means is basically if, say this is the point x, and when you draw a secant line, it goes between 2 points on a curve. So this black line here is a secant line between x and c on f. And so basically what the secant line does is it shows you how much the y values are changing on this function as you move from x to c. And if you look at the limit definition of derivative, if you take away the limit part of it, you're just doing rise over run. So you're doing the f of x minus f of c over x minus c, the output over the input. And so then the limit comes into play. And when you have the limit, you're saying that x, this value here, this point, the first point on the secant line, is getting closer and closer to the other point on the secant line. And so we're going to look at what happens to the secant line as x gets closer to c. And so as you can see, as these points which are the x value, gets closer and closer to this point c, the secant lines are changing what slope they have, which means that you're getting a different average rate of change based on which interval you're looking at. And eventually, as the secant line gets closer and closer and closer, and x is approaching c and getting closer and closer and closer, eventually it's going to be right on top of c, and they're going to be equal, essentially. And once you get there, it will no longer be a secant line, but it will be a tangent line.
So what is a secant line? A secant line touches the graph twice at 2 points. It's as though you're finding the average rate of change, as opposed to a tangent line, which only touches the graph once.
And what the tangent line gives you is not the average rate of change, but the instantaneous rate of change. And that is the derivative. So if you use this equation, you can really think of it as this is your equation for the secant line, and as x approaches c, the secant line becomes a tangent line, and you can find the derivative. So now we're going to look at the second limit definition of derivative, which is written here. When you look at this, we're going to look at the graph of f again, and here we're going to also be looking at a secant line. And here, in this one, instead of going between c and x, the secant line is going between x and x plus h. So since this is x and this is x plus h, you can infer that the space between them is called h. And so here, this y value would be f of x, and this y value is f of x plus h. When you look at the second limit definition of derivative, if you ignore the limit, this one is also just rise over run of the secant line, because it's f of x plus h minus f of x, the delta y, over if you have x plus h minus x. The x's are going to cancel and you're just going to get h. So then the bottom is delta x. And so you have delta y over delta x. And in the first limit definition of derivative, the c value is getting closer and closer to x. And in this one, h is approaching 0, which means h is getting smaller and smaller. And as this h value gets smaller, the x plus h value is going to get smaller because x is staying the same, x is staying right here, and h is getting smaller. So this is getting closer and closer. So this point is getting closer and closer to that point. X plus h is getting closer to x because h is getting closer to nothing. And once h is nothing, then x plus h will be right on top of x, and that will create a tangent line rather than a secant line. And what does the slope of a tangent line give you? It gives you the derivative. So now we're going to try using the limit definition of derivative to solve a problem where you are told to take the derivative of an equation. So here we have the equation that we're trying to take the derivative of, and here we have the first limit definition of derivative. So you're going to start out by carrying down the limit symbol. So the limit as x approaches c. And for the first f of x, you can just plug in 5x squared minus 3 because that equals f of x. And then you're going to subtract f of c. And basically, f of c is going to be exactly the same as this equation, except instead of x being your input, c is your input. So that would just be 5c squared minus 3. And that's going to be all over x minus c. And then you can distribute the negative here, and you're going to end up with 5x squared minus 3 minus 5c squared. And then you can see that these 3's are going to cancel, because negative 3 plus 3 is 0. And then you can factor out the 5 here on the top. And then after you take out the 5, you can see that this is a difference of 2 squares, and so you can factor that. And then you can see there, after you factor it, that the x minus c's cancel, and you're left with the limit as x approaches c of 5x plus 5c. And then, if you look at what the limit is saying, it's saying that x is getting closer and closer to c. So x and c are going to be essentially the same. And so where you see a c, you can plug in an x, and where you see an x, you can plug in a c. And so what we want to do is we want to have it in terms of x, because that's what the original equation was in terms of. So we're going to have 5x plus 5x, and you can drop the limit symbol here because you're plugging in your value, and you get 10x. So the derivative of f of x equals 5x squared minus 3. The derivative of that function is 10x. So now we're going to try taking the derivative of a function using the second limit definition of derivative. So we bring down the limit symbol, the limit as h approaches 0, and f of x plus h. So here you see that x plus h is the input instead of just x. So everywhere you see an x in this equation, you're going to put in an x plus h. And that's going to be minus just f of x. So that's just going to be as you see it written there. And that's all going to be over h. And so what I just did is I expanded x plus h squared, I distributed 5 to x and h, and I distributed the negative across x squared and 5x. And so now I'm going to try to simplify the stuff on the numerator of this. So now that I've canceled some things, we can see that there's a factor of h in every one of these terms, so we can factor out an h. And then what you can see is that the h on the denominator is going to cancel with the h on the numerator. And you're going to need this to happen because if h is approaching 0, you can't have a 0 on the bottom of the fraction. So you're going to need the h to cancel with something. And so then you're going to be left with the limit as h approaches 0 of h plus 2x minus 5. And then since h is approaching 0, then the h is going to equal 0. So you can drop the limit symbol because you're plugging in the 0, and you're going to be left with just 2x minus 5. And so the derivative of x squared minus 5x is 2x minus 5.
But that's so complicated. Isn't there an easier way to do it?
Yes.
We'll show you this in the next video.
I don't even know what just happened.
That's K-rot-E. K-rot-E.